Our next speaker is Alicia Smallwood. She's the research director at the Carboncopies Foundation, and in that capacity, she leads our technical review effort. She holds degrees in psychology and music and is a clinical research coordinator at the Medical College of Wisconsin, Milwaukee. Alicia, please feel free to begin sharing your screen to present.
So I'm here to tell you a bit today about what integrated circuit reverse engineering can teach us about reverse engineering the brain. We are hoping Ken Shirriff could introduce us to integrated circuit reverse engineering today, but he was unfortunately unable to join us. So instead, like I said, I'm going to be sharing with you what I see reverse engineering can teach us, and I'll be using a series of YouTube clips from one of his previous talks to help highlight some of these key points. So the purpose of this presentation is to make clear that reverse engineering any system involves piecing together a collection of different types of knowledge about that system. In terms of reverse engineering ICs, it is not just a matter of taking pictures of the chip and applying basic electric circuit laws. Similarly, reverse engineering a brain is not simply a matter of imaging brain structure and applying basic physical laws. So reverse engineering ICs actually starts in ways that are surprisingly similar to reverse engineering a preserved brain. First, chips need to be pre-processed to expose the layers to be imaged. This is analogous to plastination or aldehyde stabilized cryopreservation and slicing or ablation of thin layers of the brain. And once these important layers are exposed, the process continues with something called a die photo. A die is the core of a computer chip, diced from a larger silicon wafer. So a die photo is a photo of a metal and semiconductor layers of the surface of the die after the chip package has been removed. Microscope imaging is used to do this, which of course draws parallels with the imaging needed to reverse engineer a preserved brain. So let's hear a bit about what Ken has to say about these initial steps. He will first describe how to capture the photos, and then we'll touch more on the pre-processing. Siobhan, you can go ahead.
So where do these photos come from?
Do I need to stop sharing?
Javon's got it.
Okay.
Well, I use what's called a metallurgical microscope. If you use a normal microscope, the light shines from below, which works well if you're dealing with cells, but not so good if you're dealing with something opaque like a chip. So what the metallurgical microscope does is it has this big goofy light here that shines down through the lens. So you end up with this intense light source from above, which lets you see the features of a chip really well. If you want to look at a chip, you can use a regular microscope and kind of shine a flashlight from above. And, you can see a lot of it, but it works a whole lot better with, the specialized microscope. You can spend tons of money on microscopes, but I got this one on eBay for a couple $100. Once I have the microscope, I take a whole bunch of pictures of a chip, and then I tile these together using a program called Huygen. It's got a little bit of a learning curve. My first attempt, I ended up with this sort of Picasso-style cubist chip. One secret is make sure you have a way more overlap between successive images than you think you need, because that overlap is what lets it tie the photos together. So once I got that straightened out, here's a die photo I took of the, this is a Motorola interface chip. This chip was used in the Apple I, among other places.
The next step involves identification and labeling. Can you hear me?
Yes, we can.
Okay,
Sorry.
good.
I'm about to respond because I always have to unmute to.
Yeah, I won't ask anymore. I'll trust it. In the next clip, Ken looks at the Z80 chip. Try to notice how he uses prior knowledge of input and output connectors and prior knowledge of how to interpret the signals to understand how the chip functions. You'll see that this is a seemingly simple step that yields a great amount of data and highlights the importance of developing a database of knowledge of the different players in the brain and how they communicate.
So with the Z80. Any Z80 fans out there? All right, awesome. So this 8-bit CPU, here's a die photo I got from Zeptobars. Let's see if this laser pointer works. So when you look at this chip at first, you may think this is just like a crazy jumble of circuitry. What's going on here? Well, there's some ways you can figure out what's going on. These little squares around the outside, those are the pads that connect to the external pins. You'll notice that a lot of them have these green squiggly things. Those are driver transistors for the outputs. You can notice some big pads here for ground and power. And so once you've figured that out, that gives you a bunch of landmarks that you can use to look at the data sheet. And then you can label all the pins. And this gives you a huge amount of information about what the chip is doing. So you can see up at the top the control pins. So that lets you know that the circuitry up there is the control circuitry. You've got address pins around here. You follow those pins and you discover the address bus runs along here. Maybe I should move this over. I'm not sure I can see you guys over there. Data pins, you can follow them to the data bus, which runs through here, connects to these blocks here, connects to this block up here. So already, even at this level, we can figure out a lot of what's going on in the circuit.
So you saw there how he could identify something that he recognized within the circuit, saw what it connected to, and then was able to identify that. So he identified the address pins, and then could find the address bus, and then the control pins led him to the control circuitry. So knowing just a small piece about the structure and function of one part of the chip allowed him to understand more about the overall function of the chip and more about the function of other specific parts of the chip to which it is connected. He does some further identification by differentiating the appearance of different materials in the photo of the Z80 chip. By analogy, in images of brain slices, you want to identify features that belong to different components of the tissues like axons, dendrites, blood vessels, glia, etc., which can be done on the basis of reconstructed 3D shape, but sometimes helpful differentiators are introduced like immunohistochemistry staining. Let's take a look.
Here, and those we can look at in more detail. First block is the register file, and whenever you see a bunch of repeating patterns like this, each one of these little blocks is one bit of storage. And so this is the Z80's internal registers. If you count down, there's 16 blocks, so it's a 16-bit register pair. So each column is a separate register. Over here, we know the address lines are connected, so we can figure that this must be the program counter and the incrementing circuit for the program counter. And then the data bus is connected over here to read out the registers. If you go into a little more detail, there's some interesting things I found. There's secret registers, WZ. These are used internally, even though they're invisible to the programmer for internal storage. Another thing is the Z80 has a couple instructions that will swap the data in registers. And it turns out that it's actually not moving the data between registers. Instead, it swaps the control lines at the top. So it's much faster than actually moving data between registers. So just one of these optimizations that you find inside a chip. The next thing that you see in a lot of microprocessors from this era is called the PLA for instruction decoding. That's this block up here. The way this works is the data bus, we figured out, comes in here. The instruction register holds the instruction. The bits of the instruction flow back and forth across here. Each transistor will match a bit in the instruction. So what you end up with is, something like, say, 001 indicates a load. That will generate a control line coming out. Other things will match all the different instructions. So this is where the matching between the instruction set and what actually happens in the chip happens. And so instruction sets get designed so that it's easy to get from a bit pattern into what's happening. The third interesting block is the ALU. This is where things actually happen in the chip, the addition, subtraction, bit operations. Most chips use a bit slice, so they'll have, for an 8-bit processor, 8 stacks of circuitry, one handling each bit of the data. Now, the bizarre thing I found in the Z80 is that you can see there's only 4 slices here. The Z80 is an 8-bit chip, but it only has 4 bits of ALU. How does that work? Well, it turns out that the performance of the Z80, the designers realized it was limited by memory speed, so they had enough time they could run everything through the ALU twice. So they saved space by putting a 4-bit ALU into an 8-bit chip.
The next step involves applying abstract but well understood functional models of the various transistors and the basic circuit constructs. In this clip, Ken acquaints us with the abstract models and shows us how they can be applied to further understand the Z80 chip.
Learn more, we have to dive down into the transistor level. So I'll give you the quick description of MOS transistors. For our purposes, we can consider it basically a switch. And when the gate is on, we'll connect the source and drain. When the gate is off, they're disconnected. On the silicon, we have a silicon layer, which is basically insulator. Parts of it get diffused with impurities such as boron to become conducting semiconductor. There's a polysilicon gate on top, separated by a small insulating layer. When the gate is on, due to semiconductor magic, it makes this part conduct. And when the gate is off, this is not conducting and they're disconnected. A couple interesting things. This thin oxide layer is why MOS transistors are static sensitive. If you shuffle your feet across the carpet and touch the chip, the charge in the gate has nowhere to go, and it'll just blow a hole right through the oxide layer and destroy the chip. In the early days, the gate was made out of metal, so you'd have metal, oxide, and semiconductor. So that was your MOS transistor. Ever since about 1970, they've used polysilicon. It's really a POS transistor, but they don't use that word. Once you have the transistors, you can connect them up to form some gates. Take 2 transistors, you have a NAND gate. If both your inputs are 1, the gate conduct, it pulls the output to ground and you get a 0. Pretty straightforward. And if you have a 0 input, the transistor stops conducting and this resistor will pull the output high. It's very, very easy to implement a NAND gate with MOS transistors. When you look at a chip, it's a lot more complicated than that. We can zoom way in on the Z80 chip and we get something like this. At first it looks just bizarre, but if you stare at it long enough, it'll start to make sense. Here's what's on the chip photo, and then here's what it actually means. You can see this green region is doped silicon. We have these things that look like metal on top. That's the metal layer of the chip that connects stuff up, provides 5 volts and ground to the gate. The inputs are polysilicon coming down. Wherever polysilicon crosses silicon, it turns into a transistor. So you see that you have your 2 transistors for the NAND gate here. And then the pull-up resistor is actually implemented with a transistor because resistors are just awful. So if you stare at these chip photos long enough and closely enough, you can figure out all the transistors, figure out the circuitry. It's a little tedious. It's easier if someone like the Visual 6502 team goes in and has people who digitize all these things into polygons, and then it's much easier to extract the transistors and the circuitry. So it's not all NAND gates though. It's just as easy to build a NOR gate by putting the transistors in parallel. Now, if any transistors turned on, your output is grounded. If all inputs are 0, then it gets pulled high. So that seems straightforward enough. But the designers of the Z80, they wanted to optimize things, so they made a whole bunch of crazy gates. Here's one of the gates in the ALU. It's a little hard to follow the diagram, but transistors 1, 2, and 3 connect to this yellow metal strip. Then if 4 and 5, one of those connects the metal strip to the output, so that gives you this circuitry. And then 6, 7, and 8 are transistors in series, and so that gives you a second part of the gate. So when you put this all together, you end up with a single gate on the chip is logically 5 different gates. So it makes things very efficient. These 2 gates are actually, you don't require any circuitry. They're just made by wiring the 2 parts together. So this is one of the ways that made the Z80 much more compact. I won't try to explain what this is actually doing, other than it takes ALU inputs B and C and then computes the right operation, all with this one gate. So ALUs are really interesting because every chip does things differently. You might think you just take an adder, you take AND gates, and you get the logic you want, but it's all highly optimized. Because it's repeated 4 or 8 times, they try to squeeze out every bit of circuitry they can. The 6502 does things totally differently. So I've written more information on the Z80 and ALUs if you want that there. So that's the Z80.
So you saw there how Ken was able to make sense of an overwhelming number of kinds and squiggles number and kinds of squiggles by applying basic models of transistors and circuits. He was even able to identify some very complicated, unusual, and novel circuitry because of this basic knowledge and abstract models. And these models are analogous to understanding the contributors to the response function of a specific class of neuron or synapse, and to understanding commonly encountered neural circuits. What IC reverse engineering then suggests is that our basic models for understanding neurons and neural assemblies are key bits of knowledge that we can use to further label and identify parts of the system. In the next clip, Ken shows us how he was able to use the key steps of labeling and application of abstract models to read the program bits in the ROM, and how by reverse engineering the instruction set was able to build a simulator for the chip on which to run the program.
So that's the Z80. Now I'll move on to an interesting calculator, the Sinclair Scientific. The idea there was Texas Instruments made this cheap calculator chip in the 1970s. It had 320 words of instructions in it. They could barely fit 4 functions into that: addition, subtraction, multiplication, division. Sinclair took this same chip and then reprogrammed it to be a scientific calculator with logs, anti-logs, trig, inverse trig. And the mystery is, how can you take a chip that can barely multiply and make it into a scientific calculator? So I decided to find out. So thanks to John Rick Master, I got this die photo of the calculator chip. You can see a lot of the same features that showed up in the Z80, the pins around the outside, ALU up here in the corner, decoding PLA, the regular register grid. It also has some things you don't see in the Z80, such as 7-segment display drivers. But the most interesting thing for us is the instruction ROM here in the middle, which holds the code that the calculator runs. If you zoom way in on it, you can actually see the individual bits on the chip in the metal layer. And so by looking at this very carefully, I was able to pull out the code that the calculator is running. Then I was also able to reverse engineer the instruction set it's using. And so I built a simulator for the calculator. So this simulator, you can try it out online if you want. It runs the exact code of the calculator. I then reverse engineered the algorithms that worked and discovered how they managed to cram all this into such a small chip. And I discovered there were 2 tricks. The first trick is that because they used scientific notation and they used RPN input, they're able to save a whole lot of code on the chip. And then they used that extra space to put in these really, really compact, but really slow and inaccurate algorithms for the scientific functions. So for instance, for trig functions, they do repeated rotations by 1/1000th of a degree until you get to the angle you want. Because it's a decimal calculator, dividing by 1,000 is just a trivial shift. You do a shift and then add and subtract. You just repeat that as necessary, and you can get your sine, cosine, inverse operations. One side effect of this is that the bigger the angle you put in, the slower the calculator. It just has to keep going until it gets to the angle. Similarly for logs, they used an algorithm with powers of 0.99 in a decimal machine. That's really easy too. You just shift 2 digits to divide by 100, and then you subtract and repeat as necessary. So that solved the mystery of how they managed to get scientific calculator out of a regular calculator.
So here we saw how understanding what the simulator is doing depends on what each instruction performed means, as well as interpretation of the bit representation of numbers. That level of understanding meant that he was able to uncover the tricks used for scientific calculator calculations. And he was also able to explain characteristic behavior, such as taking much longer to calculate cosine of 100 compared to cosine of 10. So in terms of reverse engineering the brain, this is similar to understanding characteristic behaviors from knowing what a brain function is trying to do and how it is implemented in the brain. IC reverse engineering suggests that we might be able to do this with the brain by having a basic understanding of its parts. Next, Ken takes a look at analog chips by looking at the 555 timer. And analog systems, specific system operations are achieved by designing a lot of unique component architectures, nothing like the abstract models. And this is similar to the many specialized classes of neurons with class-typical responses, and every neuron has its own unique shape and level of detail.
I'd like to move on to analog chips. Anyone here ever used a 555 timer? Yeah, pretty much all of you. So this is one that I cut open. Before I get into the details of that, I should talk a little bit about bipolar chips, bipolar transistors, the NPN and PNP transistors that get used. You're probably familiar with how NPN transistors, you've got a layer of N, layer of P, layer of N, base is connected in the middle. But the thing is, when you look at ICs, it's nothing like that, just totally different. Here are some real bipolar transistors from ICs. Often you have your emitter in the middle. Sometimes it's like a right angle. Sometimes you've got 2 emitters. Sometimes you've got 6 collectors and you can't even find the base. It just gets really strange when you look inside an IC. So to explain what's going on a little more, here's a dye photo of an NPN transistor, and then here's the cross section. As you can see, it's much more complex than the MOS transistor, which is why the world has mostly moved off bipolar transistors. If you look down from the emitter, you can see the N, P, N layers are stacked vertically, but the connections are very different. To figure out what's happening in a dye photo, the emitter usually has this multiple circles. The base, you can see this faint outline here of the P layer, and then the collector is off to the side somewhere. Now you might think that a PNP transistor, you just switch everything around, but it turns out they have a totally different structure. It's more of a circle structure. Here you can see the P, the N, the P. So you do have the PNP layers, but physically the emitter is this little dot in the middle, surrounded by the base, and then the collector is off to the side, wrapping the whole thing. And then the base connection goes way underneath and comes out the other side here. It's so far away that they actually run another wire, through the middle of their transistor to help the layout. So now that you know what to look at, here's a dye photo I took of the 555 timer. You can see the circular PNP transistors. You can see tiny rectangular NPN transistors, the bond wires around the outside, 3 giant transistors to provide the high current output.
So we see here again the necessity for prior knowledge of the abstract model of PNP transistors, but the real ones look nothing like the abstract models. There are lots of different shapes and organizations, much like there are tons of variations of neuron classes and how all neurons are unique. So though basic models are helpful and applicable even when facing circuitry that is uncommon or largely unfamiliar, we need to keep in mind that the models we have won't tell the whole story. There is still some understanding of the structure that will be difficult for us to predict and therefore may need to be gleaned throughout the reverse engineering process. So overall, there is a lot of that IC reverse engineering can teach us about how to go about reverse engineering the brain. We need to be able to label major parts of the brain to help understand how they function and interact. And we also need abstract, well-understood models of the parts to help us identify structures in slice imaging data and to better understand more complex structures. I hope this leaves you with a decent idea of the parallels between reverse engineering integrated circuits and reverse engineering the brain, and inspires you to expand your horizons when thinking about reverse engineering the brain by exploring similar tasks in other academic fields that might provide clues on where to move next with your research. Do we have any questions?
Thank you, Alicia. Yeah, that was really interesting. I actually got an interesting question came in online, and I have a few as well. I'm just going to say, first of all, that it's interesting to me to see when you look at what the folks doing this reverse engineering and integrated circuits are doing, how much deep knowledge about integrated circuits themselves in general, about the materials, about how they interact, all of this comes into play when doing the reverse engineering. It's not like they're just reading something off and then, out comes the simulation. Let me just pop up a question that came in online first. Leslie Seymour asks, how much value would be provided, or how much value would you get from reverse engineering entire hardware, firmware, software systems, including network configuration, user behavior, and application context based on an incomplete technical documentation and execution logs of a benchmark makes vis-a-vis reverse engineering the brain of a specific person? And I'll try to clarify that a little bit. I think what he's trying to say is, if you look at what we're trying to do in the brain, it's kind of like you're trying to do a reverse engineering of an integrated circuit, and you have available to you this hardware that's there, and maybe you have some software somewhere, but you don't know a lot about what you're supposed to do. You don't have the technical manual that tells you what the instruction set looks like, or things like that. So how much do you think this compares?
I think it's pretty obvious how easily it compares. It's almost the exact same process, right? I'm not very techie, so some of these terms are a little vague to me, so I'm not sure I can give a very good answer to this.
All right, let me open it up to the room. Anyone have anything reverse engineering, IC reverse engineering related to ask? Okay. I think there was another question that came in online. I have another myself too. No, I don't see it here. Maybe that was just a reorganization of the Q&A form. Yeah, I guess since this was an analogy, it's hard to ask specific questions about what this means for brain reverse engineering, besides just to point out that there's a process involved, and that at each step of that process, information is brought in, and that information isn't necessarily just something you're staring at when you look at the surface of the chip, but it can be other things, other pieces of information you're bringing in to make the reverse engineering process possible.